All right, hello everyone. How's everybody doing today? Good to see you, so to speak. And welcome to my channel. This is an educational channel, and we look at uh, various theories of everything and the like, all-encompassing theories, things that you can apply to a holistic worldview and a holistic lifestyle. And today is our 375th video on the reciprocal system of theory from Dewey Bernard Larson. And Mr. Larson was an engineer who lived in the 20th century, died in 1990. Around 1959, he proposed his two fundamental postulates about the nature of the universe. And then for the next 30 years, he went through a process of deduction to take his fundamental postulates and turn them into a theoretical universe. How, if his postulates are correct, what kind of a universe would that entail? And then in his books, he compared his theoretical universe with the so-called actual universe of the legacy scientists, the one that they had measured and observed and experimented upon and compiled in their tables, scientific tables, and so on. It's a very interesting study, and he, I think, definitely validated the theory through the similarities between his findings that came strictly from theory and the findings that the scientists had come to through observation in laboratories. And could be that he's just fudging the numbers and making it all up and it's all a fraud. But I think if you read some Larson, you can tell that he's not a fraud. So, could be wrong, but I'm going to risk my life on the fact that I'm not. Now, the basics behind the reciprocal system, again, are laid out in his fundamental postulates. The first of the two postulates, which is by far the most relevant, is that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, so that's why he calls it the reciprocal system, because of the reciprocal relationship between space and time in motion. Space and time are reciprocals of each other, meaning that they both have the identical qualities, except they have them in reverse. Kind of like, the reciprocal of 1/4 is 4/1. They have the same 2 qualities, 4 and 1, but they have them in the different order above and below the fraction. Motion is a fraction where time or space is the numerator and space or time is the denominator. But space and time can also come in multiple dimensions, like acceleration. Acceleration is space over time to the second power. I dropped the rock out of the window and it fell at 32 feet per second. That's 32 feet of space in 1 second per second of time. Space over time to the second power. And all of our scientific entities are also likewise just exclusively relationships between space and time. Fractions with space or time as the numerator, time or space as the denominator. Another thing about reciprocals is they multiply to be 1. 4 times 1/4 equals 1. And so 1 is at the center of a reciprocal system, whereas 0 is at the center of the legacy science system. The legacy scientists measure their speeds from 0 speed. Larson measures his from what he calls unit speed, and that comes from the discrete unit clause within this first postulate. Space and time, and therefore motion, exist in discrete units. That means that there is a minimum unit of space and a minimum unit of time. If you don't have that full minimum unit, then you don't have anything. And if you have 1 unit of space in 1 unit of time, you have the speed of light. The speed of light is what Larson calls unit speed. 1/1 equals 1. And this unit speed is the null point, or the 0 point, or the origin, or the reference point of this universe, the state of rest. Now, this motion is also what you call a scalar motion. And you would be able to envision a scalar motion if you take a balloon and you put some dots on it, and then you blow up the balloon. All of the dots are moving away from each other. That is a scalar motion, meaning that it is a motion that has a magnitude, but it has no specific direction. Most of the motions that legacy scientists talk about are in the category of velocity, motion with a vector in a specific direction. But Larson's scalar motion is not like that. It's just, it's not a motion in space in any particular direction. It's really just the expansion of space itself. And so too with time. Time is always getting later and later and later and later, but in no specific direction. Space is always getting farther and farther and farther apart, but in no specific direction, when left to its own. And so this speed of light is always getting farther and farther and farther apart in space, and later and later and later and later in time. That is the state of rest of this universe. And then you make measurements based on the difference or displacement from that speed of light moving outward in all directions. And Larson refers to that as clock time and clock space. And then the three-dimensionality of space and time he refers to as coordinate space and coordinate time. And he was able to basically induce, or through inductive reasoning, recognize that space was three-dimensional. And so time also, therefore, is three-dimensional as being a reciprocal of space. All the qualities that adhere to one adhere to the other. And so we have 3 dimensions of space, 3 dimensions of time. And we have this speed limit, not so much of a speed limit as a speed boundary of the speed of light, which means that half the universe is moving faster than the speed of light, and half is moving slower than the speed of light. Larson refers to these as the cosmic sector and the material sector, respectively. The legacy scientists really only know anything about the material sector. In fact, Einstein said that the speed of light is the maximum speed of the universe, basically denying the cosmic sector in its entirety. But the legacy scientists can catch up quickly because the cosmic sector is actually identical to the material sector, except that it's reciprocal, meaning that space and time roles are reversed. So in the material sector, you have coordinate space, 3 dimensions of space, and you have clock time. The clock is always getting later and later and later and later. We're familiar with that world. But when we cross that speed of light boundary and we move into the cosmic sector, then we experience coordinate time, 3 dimensions of time, and clock space. The space is always getting farther and farther and farther apart. So that's basically how it works. And, then Larson, through a long process of deduction, was able to come up with his theoretical universe. Now, about a year ago, almost a year ago now, I did about 15 videos on Larson's deductive development of the reciprocal system. It's called The Outline of the Deductive Development. So if you want to go back and watch those videos, you'll get an idea of Larson's thinking, his thought process about how he came from that postulate along with the second postulate, which is simply that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. I personally would dispute quite a bit of that second postulate, and I've been convinced of that by Dr. Bruce Perrett, one of his revisers, especially after Larson died. But regardless, the first postulate is by far more important. And so Larson deduced his theoretical universe from those postulates, and I go over all of that in those videos. Now today we're going to go in response to the paper from yesterday, where we looked at KVK Nehru, another one of Larson's acolytes. He was talking about the fundamentals of science in the what did he call it? The Aquarian age, and talked a little bit about kind of the future, where the reciprocal system is headed, and so on and so forth. Now Larson talks about this as well at more length. And so this paper, I don't believe we'll get through today, but it'll take a few days. But this is a paper that Larson gave in 1978 called The New Science of the 21st Century. And the prelude here is, relativity is in trouble. Electrons don't exist. Quarks proliferate like Ptolemaic epicycles. An Enterprising New Theory by Dewey B. Larson. Keynote address at the 3rd Annual NSA Conference. That's the New Science Associates, not the government agency, at the University of Utah in Salt Lake City, 1978. And it goes like this. 5,000 years ago, the invention of writing on clay tablets by the Sumerians first enabled the human race to leave a permanent record of its thought and actions. But according to that record, there was already in existence a rather sophisticated science of astronomy. The priests, who were the astronomers of the era, were not only familiar with elementary astronomical facts, such as the apparent motions of the sun, moon, and planets, they were able to predict eclipses and to establish the length of the year to within about half an hour of its true value. The premises upon which these and other scientific calculations were made were the fundamentals of the science of that era. That is, they were the most general of the principles utilized in the scientific endeavors of that day. These principles were originally derived by a simple application of what we now call inductive reasoning. They were generalizations from experience. This is the most reliable method of arriving at general principles, fundamental or otherwise. Unfortunately, it is limited by the amount of empirical information available for analysis and by the extent to which that analysis has been carried out. An inductive science, therefore, tends to encounter difficulties in dealing with new discoveries. In time, it accumulates an embarrassing backlog of unsolved problems. This was the situation that confronted the ancient sciences of Babylonia, Egypt, and the Far East some 3,000 years ago. Okay, this section is called The Golden Age of Greek Science. The time was ripe for some new approach, and this was provided by a remarkable group of thinkers flourishing in Greece during the golden age of that country's history. The source of order in the universe, these men said, is mind, and consequently the proper method of arriving at the governing principles of the universe is to apply insight and reasoning. The intellect, said Plato, is our only means of seeing the truth. The result of the new policy was to change the emphasis on scientific inquiry and to concentrate on the causes of physical phenomena rather than on the phenomena themselves. Where the Egyptians saw only the bare fact that a rock falls if it is released from a height, the Greeks looked for the cause of the fall and invented a theory to account for it. Everything has its natural place, the Greeks concluded, and the falling rock is merely seeking its natural place. By providing an explanation for the fall of the rock, the Greeks remedied the deficiency that counted so heavily against the earlier inductive sciences. Similarly, they reasoned that while the earth is obviously imperfect, the heavens are perfect. All motion in the heavens, therefore, takes the perfect form, that of a circle. It follows that the orbits of the planets are circular. Although observation and measurement were definitely relegated to subordinate positions in Greek science, they were not disregarded entirely, since observation showed that the planetary orbits are not, in fact, quite circular. Greek astronomers recognized that there was an awkward discrepancy here. But one of the strong points of the Greek method of deriving scientific principles by pure invention is that it lends itself readily to the assimilation of new information by means of more invention, additional ad hoc assumptions. The discrepancy with respect to the motions was removed by the addition of small circles or epicycles to the planetary orbits. Then, when further observations disclosed further discrepancies, these were handled in the same way, by adding more epicycles. This section is called Troubles with Ptolemy. The Ptolemaic theory of planetary motions is typical of inventive theories in general, since we are able to see it in the light of historical perspective. An examination of this theory gives us a good view of the logical status of all inventive theories. The first point to be noted is that the theory was mathematically correct within the then current limits of observational accuracy. This is true of the inventive theories in general because they are deliberately designed to fit mathematical relations already known. The second significant point is that the Ptolemaic theory was conceptually wrong. Its interpretation of the mathematics was not correct. This, too, is an inherent characteristic of invented theories. They are all conceptually wrong because of the circumstances under which they originate. As many observers have pointed out, Scientific problems do not remain unsolved because of a lack of technical competence on the part of those who are trying to solve them, or because the methods available for dealing with them are inadequate. The lack of success, where it exists, is due to the absence of some essential piece or pieces of information. In the days of the ancient Greeks, two such items were missing from what was known about the planets: the fact that the planets revolve around the sun rather than around the earth, and the existence of a gravitational force controlling the motions. Without these two pieces of information, the Ptolemaic theory could never be conceptually correct, no matter how many epicycles were added. The point that I want to emphasize is that the same considerations apply to all inventive theories. If the essential information is available, it is not necessary to resort to invention. The needed theories can be derived inductively. If the essential information is not available, the theories that are invented to agree with the known mathematical relations cannot be conceptually correct. This section is called Too Many Epicycles. In view of the practically unlimited opportunities for making additional ad hoc assumptions to meet any situation that may arise, an inventive science never reaches the kind of a situation that causes the downfall of inductive sciences. At any given time, there may be a few items for which plausible explanation has not been yet invented, but there is never the large accumulation of unexplained phenomena that characterizes an inductive science that has fallen behind the progress of empirical investigation. However, the freedom to meet new requirements by adding more and more ad hoc assumptions or epicycles leads to a fate of a different kind. The time ultimately comes when such a theory simply has too many epicycles. In the meantime, even though the fundamental theories in current use are inventive, the accumulation of empirical information and the construction of inductive generalizations of a lower rank continues. Ultimately, a point is reached where the principles derived inductively are sufficiently broad in their scope to challenge the premises of the prevailing theories. The Greek system reached this point about 500 years ago. Since then, reverted to science, not since. Science then reverted to the inductive status, discarding inventive concepts such as the perfection of the heavens and the natural places of physical entities in favor of principles formulated by such men as Kepler and Newton through inductive reasoning from observed and measured facts. This section is called The New Science. With the benefit of all the empirical information accumulated during the approximately 2,500 years since the demise of the earlier inductive systems of ancient civilizations, the new inductive science was a vastly improved product. It scored some remarkable successes. At one time, its practitioners were quite confident that a complete understanding of the universe was within their grasp. But here again, the inherent inability of an inductive system of theory to keep pace with the progress of empirical discovery asserted itself. Eventually, Newtonian physics was confronted with a series of discrepancies for which it had no plausible answers. Another reversal of policy took place. The inductive science of Newton and his contemporaries was replaced by a science based on invented principles, just as the first inductive sciences were replaced 3,000 years earlier by the inventive system of the Greeks. When an idea or system of ideas gains general acceptance and becomes a familiar feature of current thought, its origins recede from view. It is quite likely that many a reader may be reluctant to believe that the basic theories of modern physics, the relativity theory, for instance, belong in the same category as the Ptolemaic theory of astronomy. But both are pure inventions. The originators of the modern theories do not deny this. Indeed, they emphasize it. Einstein, for example, saw the general acceptance of his theories in just the way that I have described, a victory of inventive science over inductive science. In his opinion, pure invention is the only way in which true fundamental principles can be derived. Einstein was highly critical of Newton's attempts to derive such principles inductively. He said this, quote, Newton believed that the basic concepts of and laws of his system could be derived from experience. The tremendous practical success of his doctrines may well have prevented him and the physicists of the 18th and 19th centuries from recognizing the fictitious character of the foundations of this system. Einstein's own view was that the, quote, basic concepts and laws of physics, end quote, which what I am calling the fundamentals, are, quote, in a logical sense, free inventions of the human mind, end quote. He elaborates this view in those statements taken from his book, The World as I See It. Quote, since, however, sense perception only gives information of this external world of physical reality indirectly, we can only grasp the latter by speculative means. The theoretical scientist is compelled in an increasing degree to be guided by purely mathematical, formal considerations in his search for a theory, because the physical experience of the experimenter cannot lift him into the regions of highest abstraction. And another quote is, the axiomatic basis of theoretical physics cannot be extracted from experience, but must be freely invented. This is a rather general tendency to assume that there is a rather general tendency to assume that Einstein and the other architects of modern science were not actually as casual about the background of their theories as these words would indicate, that their basic principles must have been anchored to something solid at some point. But this is not true. As Rudolf Carnap puts it, these theories were, quote, constructed floating in the air, so to speak, end quote. Einstein gives us enough information about some of his concepts to make it clear that when he talks about free invention, he means exactly that. For example, the propagation of radiation plays a very important part in his theories, and his comments about the explanation that he invented to account for the mechanism of propagation and its relation to space are therefore very significant. In one of his books, he tells us that the formulation of a theory to account for this phenomenon is a very difficult task, and he concludes with this statement, quote, the only way out seems to be to take for granted the fact that space has the physical property of transmitting electromagnetic waves, and not to bother too much about the meaning of this statement, end quote. The point of all this is that the invented theories of present-day science have exactly the same logical standing that the Ptolemaic theory of astronomy, the natural place theory of gravitation, and the other theories invented by the Greek scientists had in their day. They are mathematically correct, but conceptually wrong. This statement may seem to be in direct conflict with many confident assertions in scientific literature that the fundamental theories of modern physics are established beyond the shadow of a doubt. But if one examines the basis for these assertions, one finds that the evidence cited is purely mathematical. What has been established is that the theories produce the correct mathematical results. Like all other inventive theories, they have been specifically designed to produce these correct results. But none of them is unique. In each case, there are alternatives that produce the same result. And as Richard Feynman points out, there is no scientific criterion by which we can choose between any two of these alternatives, because they both agree with experiment to the same extent. So two theories, although they may have deeply different ideas behind them, may be mathematically identical, and then there is no scientific way to distinguish them. He goes on to say, every theoretical physicist who is any good knows 6 or 7 theoretical representations for exactly the same kind of physics. And that is a quote from Richard Feynman. And that's where we're going to stop for today. We will start up tomorrow with a section that is called, Is Invention Necessary? And thanks for tuning in today. And please come back tomorrow, catch the rest of this article, or at least the next installment, and have a great